The following static charges with a magnitude of q are positioned in a square configuration at a distance d from each other. And we're asked to first write an equation for the force exerted by charge 4 on charge 1. So we know the electrostatic force is a vector, and it's equal to 1 over 4 pi epsilon naught multiplied by the magnitude and sign of both charges. So that will be minus q by q over the squared distance between them. So they're at a distance d from each other, so we get d squared. And the negative sign indicates that the force between these charges is attractive. Now part B asks us to determine the magnitude and direction of the electric field in the middle of the square. Well, the electric field vectors of the positive charges point away from the positive charge. And for the negative charges, the electric field vectors point towards those charges. So in this case, the magnitude of all the charges is equal. So by observation, we can observe that this vector is going to cancel this one, and this vector is also going to cancel this one. And using the superposition principle, that the electric field vector is equal to the superposition of the electric field vectors of each of these charges. So we sum from charge 1 to charge 4, and we have the electric field vector of each charge. So therefore, by observation, we can see that by superimposing those 4 vectors, we get a 0 vector at the midpoint between those charges. Now part C asks us to determine the magnitude and direction of the electric field midway between charge 1 and 2. So let's just copy those down here. And let's draw the direction of the electric field from this point to each of the charges. So the electric field vector points towards the negative charge and away from the positive charge. And it also points away from positive charge 4 and towards charge 3 because it's negative. And let's denote this angle as theta, and by symmetry this angle is also going to be theta. And now we can superimpose these vectors. So in the horizontal direction, we have the magnitude of the electric field vector of charge 4, cosine theta gives us the horizontal component to the left, and then plus the component of the electric field vector of charge 3 in the horizontal direction. And in the vertical direction, we have the electric field vector of charge 1 pointing upwards, and then plus E2 in the vertical direction, and then minus E4 sine theta, and then minus E3 sine theta. Gives us that component pointing downwards. Now we can observe that the distance to charge 4 from this point is the same as the distance from charge 3 to this point. And similarly, the distance from charge 2 and charge 1 to this point is the same. So they're going to have the same magnitude, aren't they? So to simplify our calculation, we can write 2e1 minus 2e4 sine theta. And we can also observe that because the magnitude of E4 is equal to the magnitude of the electric field vector of charge 3, and the angles between them and the horizontal is the same, so what we get is 0 in the x direction. And in the y direction, we can use some geometry to get sine theta. So that would be the opposite dimension, which is d on 2, over the hypotenuse. So the hypotenuse is going to be equal to the square root of d squared plus d on 2 squared. And if we factor out d squared, we get root d squared is d, and the d's cancel straight away. So what we're left with is 1/2 over the square root of 1 plus 1/4, or 4/4 plus 1/4, which is 5/4. And what that gives is root 4 is 2, and that goes in the numerator where the 2's cancel, and we end up with 1 over root 5. And now we can compute the electric field of charge 1. So we have 2 multiplied by 1 over 4 pi epsilon naught, multiplied by that charge, which is Q, over the squared distance between this point and the charge. So that would be d on 2 squared. And note that we're not using negative signs for the charge, because we've already accounted for the direction in this summation in the y direction here. And then we have minus 2 by 1 over 4 pi epsilon naught. And the electric field vector of charge 4, we have Q over this length over here, which we've established is equal to this. So what we'll have is the square root of d squared plus d squared on 4, which is 5d squared on 4, and that's all squared. And that's of course multiplied by sine theta, which is 1 over root 5. And now we can just cancel out this square root, all squared, and we can simplify our calculation here. So 2 squared is 4, which will cancel with this 4. So we end up with 2q over pi epsilon naught d squared. And then we have minus 4 on 4 cancels. So we get 2 multiplied by q over pi epsilon naught. And then we have 5 by root 5 d squared. And we can do a bit of a further simplification. So we have 2q over pi epsilon naught d squared. And on the left hand side we have 1 minus 1 over 5 root 5. So because the electric field has a 0 horizontal component, this here is actually the magnitude of our electric field vector. And the net direction is going to be upwards.